Welcome to all of you. Now we discuss paper CC-9 2021 Group C Multivariate Calculus Semester 4 Mathematics Honors. Question paper 2021 paper CC-9 Group C. Question 7. Using differentiation under the sign of integration, prove that integration 0 to pi by 2 log bracket a cos square theta plus b sin square theta d theta equal to pi log of this a b greater than 0. This question may be wrong because this part answer is this. This is the answer. This integration 0 to pi by 2 pi into bracket log bracket root a plus root b bracket close minus 1 bracket close plus pi by 2 log b by 4 minus pi log bracket root over b minus 1. This log to the base e, all log to the base e. Let f a theta equal to log to the base e a cos square theta plus b sin square theta a greater than 0, 0 less than equal to theta less than equal to pi by 2. Phi a equal to integration 0 to pi by 2 f of a theta d theta a greater than 0, where a is a parameter. Now del del a f equal to this cos square theta by a cos square theta plus b sin square theta, 0 less than equal to theta less than equal to pi by 2 a greater than 0. Since a and b both greater than 0, then a cos square theta plus b sin square theta greater than 0 in this closed interval 0 to pi by 2. So f of a theta and del a f are both defined and continuous for a greater than 0 in the closed interval 0 to pi by 2. Now we apply Leibniz rule, differentiation under the sign of integration. If f is defined and continuous on this region E, and if del a f a theta exist and continuous on E, and f equal to integration theta 1 to theta 2 f of a theta d theta, a belongs to the closed interval a1 to a2, then phi is differentiable on this closed interval a1 to a2, and phi dash a equal to integration theta 1 to theta 2 del a f d theta. E is this region, this point, this a theta order pair a theta, this real numbers. Obviously a1 less than equal to a less than equal to a2, and theta 1 less than equal to theta less than equal to theta 2. This E belongs to R2. Hence, by the above theorem, phi dash a equal to integration 0 to pi by 2 del a f d theta. So integration 0 to pi by 2 cos square theta by a cos square theta plus b sin square theta d theta. Let I equal to this integration 0 to pi by 2 cos square theta d theta a cos square theta plus b sin square theta. So I equal to 1 by a 0 to pi by 2 a cos square theta d theta whole divided by a cos square theta plus b sin square theta equal to 1 by a integration 0 to pi by 2 bracket 1 minus b sin square theta by a cos square theta plus b sin square theta d theta equal to 1 by a integration 0 to pi by 2 d theta minus 1 by a integration 0 to pi by 2 b sin square theta whole divided by b a cos square theta plus b sin square theta d theta equal to pi by 2a minus b by a into integration 0 to pi by 2 bracket 1 minus cos square theta d theta whole divided by a cos cot theta plus b sin cot theta equal to pi by 2a minus b by a integration 0 to pi by 2 d theta by a cos cot theta plus b sin cot theta plus b by a integration 0 to pi by 2 cos cot theta d theta whole divided by a cos cot theta plus b sin cot theta, and this equal to I. So we put b by a into I here, pi by 2a minus b by a integration 0 to pi by 2 dividing on both sides numerator and denominator by cos cot theta. So we get from this integral sec cot theta d theta divided by a plus b tan cot theta. For this second integral, put this b tan cot theta equal to z square. So we get 1 minus b by a into bracket I equal to pi by 2a minus b by a integration 0 to infinity, because when theta equal to pi by 2 z tends to infinity, dz by square root of b into bracket a plus z square. Limit a tends to infinity, integration 0 to a dz whole divided by root a whole square plus z square, and this is equal to limit a tends to infinity 1 by root a tan inverse z by a, lower limits and upper limits 0 and a. So we get limit a tends to infinity tan inverse a by square root of a equal to pi by 2a minus 1 by a square root of b by a into pi by 2. So taking common pi by 2a, we get bracket 1 minus root over square root of b by a. So this a minus b by a into I equal to pi by 2a into square root of a minus square root of b by square root of a. This a minus b, you can write square root of a whole square minus square root of b whole square. So square root of a plus square root of b into square root of a minus square root of b. Cancel from numerator and denominator, square root of a minus square root of b, because a not equal to b. So pi by 2 whole divided by 2 square root of a into bracket square root of a plus square root of b. From 2, pi dash a equal to pi by 2 square root of a square root of b. From 2, this is 2, this phi dash a is equal to I. So phi dash a equal to actually I. So you can write this equal to phi dash a. Integrating, we get above phi a equal to pi by 2 dA by square root of a into bracket square root of a plus square root of b plus c. C is an arbitrary constant, integrating constant. Now we can write this 1 by square root of a minus 1 by square root of a plus b square root of b, because after simplification we get square root of b whole divided by square root of a into bracket square root of a plus square root of b. So dividing by square root of b, we get this pi by 2 square root of b integration dA by square root of a minus integration dA by square root of a plus square root of b plus c. For the first integral, put square root of a equal to z. So integration twice z dz by z, and for the second integration, put square root of a plus square root of b equal to p. So we get integration 2 into bracket p minus square root of b into dp whole divided by p plus c. After integration from this 2, taking 2 common, and this is the denominator 2, so cancel 2 from numerator and denominator. This integration z and this integration p by p, so this 1, so integration dp minus minus plus square root of b and dp by p plus c. So p, value of p is square root of a plus square root of b, and this square root of b into log of square root of a plus square root of b plus c. Cancel square root of a minus square root of a minus b. So taking common square root of b common, log of square root of a plus square root of b minus 1 plus c. So we get phi a equal to this. Now from 1, phi 0 is equal to 0 to pi by 2 log to the base e b, all log to the base e here in this question, b sin square theta d theta, taking a tends to 0 plus since phi is continuous for a greater than 0. From 1, this equation 1, phi a integration 0 to pi by 2 log of a cos square theta plus b sin square theta d theta. So taking phi 0 a equal to 0, so we get this log of b sin square theta d theta. So log b plus 2 into sin square, from this square 2 into log of sin theta d theta. This is the log b constant, so d theta integrating theta from limits from 0 to pi by 2, so we get pi by 2 into log of b to the base e plus 2 into this integration 0 to pi by 2 log of sin theta d theta equal to pi by 2 log of half to the base e. This star notation because we calculate this integration in the note this. So pi by 2 common log b plus log of 1 by 2 whole square. So this is 1 by 4. So b by 4 here. And from 3, phi 0 equal to phi 0 is equal to limit it is to 0 plus phi of a. So from 3, this phi 0 is equal to 0 pi log of square root of b minus 1 plus c. So this is phi 0 and this also phi 0, equating both. This c equal to pi by 2 log of b by 4 minus pi log of the square root of b minus 1. Hence phi a equal to, phi a means this integration 0 to pi by 2 log of bracket a cos square theta plus b sin square theta d theta equals to, from 3, this pi into bracket log of square root of a plus square root of b minus 1 plus c, and value of c is this. So this pi by 2 log of b by 4 minus pi into log of square root of b minus 1, and this is the answer. In this note, we calculate here 0 to pi by 2 log of sin theta d theta. This is equal to 0 to pi by 2 log of cos theta d theta equal to pi by 2 log of half. The only singularity at theta equal to 0, because if we put theta equal to 0, so log of 0 this at infinity, so for theta equal to 0 we actually negative infinity minus infinity log of 0 tends to 0 plus 0 balance, we assume the integral is convergent, and let I equal to integration 0 to pi by 2 log of sin theta d theta equal to integration 0 to pi by 2 log of sin pi by 2 minus theta d theta, because we know integration 0 to a f x dx equals to integration 0 to a f of a minus x dx, and this is equal to 0 to pi by 2 log of cos theta d theta. So 2i equal to integration this log of sin theta d theta plus integration log of cos theta d theta. Addition is valid as both the integrals are convergent. So integration 0 to pi by 2 log of the sin theta into cos theta, so 1 by 2 into sin 2 theta, so log of half to log of sin 2 theta. Now to calculate this part 0 to pi by 2 log of sin 2 theta d theta, we find this 0 0 and pi by 2 also 0. So we remove this 0 and pi by 2 and taking limit epsilon delta tending to 0 plus this epsilon to pi by 2 minus delta log of sine 2 theta d theta, and this put 2 theta equal to z, so log of sine z dz by 2, and this limit z equal to 2 epsilon when theta equal to epsilon and theta equal to pi by 2 minus delta, z is equal to pi minus 2 delta, and this log of sine z dz whole 1 by 2 into this, and when pi delta tends to 0, so we get this 0 to pi. Now we know 0 to pi 2 twice a fx dx is equal to 2 of integration 0 to a fx dx if f of 2a minus x equal to fx. Here log of sine z, so 2a, so pi minus z equal to sine z again, so we can write 2 into 0 to pi by 2 log of sine z dz, and this integration equal to I, because I choose here I equal to this. So twice I equal to pi by 2 log of half to the base c plus I. So I equal to pi by 2 log of half. Actually this problem is wrong, so we must attend in the question all questions, then you can get credit for the wrong question in the question paper. Next question, question 8. By changing the order of integration, prove that integration 0 to 1 dx, integration x to 1 by x y dy whole divided by bracket 1 plus xy whole square into bracket 1 minus y square is equal to pi minus 1 by 4. Actually this graph y equal to x, this is the straight line y equal to x, and y equal to 1 by x, so this is this y equal to 1 by x, this part, one part of the rectangular hyperbola. This the integration, region of integration here E is this in here y equal to x to y equal to 1 by x, and x equal to 0, x equal to 0, this line y axis, to x equal to 1, so x equal to 1 is this line, so this dotted region is the integration region of integration actually. Now we divide this part E1 lower part and this part E2. Clearly this E1 is the set of all those xy belongs to R2 from x equal to 0 to x equal to 1 and y equal to x, this line y equal to x to y equal to sorry, this E is the whole region, this region, so 0 to 1 and y equal to x, this, and y equal to 1 by x, and this rectangular hyperbola this, and E1 this part, this x equal to 0 to x equal to y up to this, from this part to this part, this line x equal to y, and this y equal to 0 from this point y equal to 0, this x axis, to y equal to 1, this line is y equal to 1, and E2 for this portion x equal to 0 to x equal to 1 by y and y equal to 1 to y equal to infinity. So this double integration E, we can break this double integration over E1 plus double integration over E2. So for this E1 we can write y equal to 0 to 1, because this e1, this y equal to 0 to 1, this limit, and x equal to 0 to y, this x equal to 0 to y. For this dx by 1 plus xy whole square, this into dy, whole dy. And for this part e2, y equal to 1 to infinity, y equal to 1 to infinity, y by 1 plus y square, integration x equal to 0 to 1 by y dx by 1 plus xy whole square dy. For this 1 minus 1 by xy into 1 by y, lower limit x equal to 0 to y, upper limit dy, and similarly x equal to 0 to 1 by y. So first we putting x equal to y, so 1 plus y square, and this, and next this y cancel, and next y x equal to 0 put here, so this 1 minus plus, so 1 minus 1 by y square dy. And for this put x equal to 1 by y, so this 1 plus 1 2, this minus half x equal to 0, this 1. So from this integration 1 dy by 1 plus y square, and integration 0 to 1 dy by 1 plus y, 1 plus y, so 1 by 1 plus 1 y square whole square, plus this half common, limit b tends to infinity, y equal to 1 to b dy whole divided by 1 plus y square. Now for this first integral, this tan inverse y, limit 0 to 1. For this second integral, put y equal to tan theta. So when y equal to 0, theta equal to 0, y equal to 1, theta equal to pi by 4. And this dy equal to sec square theta d theta, and this 6 to the power 4 theta, plus for this part, limit b tends to infinity tan inverse y 1 to b limits, this is equal to pi by 4. This tan inverse 1 is pi by 4, and tan 0 0, minus half this 1 by cos square theta. So this we can find 1 plus cos 2 theta, 1 plus cos 2 theta d theta is half, limit b tends to infinity tan inverse b minus pi by 4 tan inverse 1, for this tan inverse 1. Because this is the 1 by sec square theta. 1 by sec square theta means cos square theta. So we can write 1 by 2, 1 plus cos 2 theta. Integrating we get theta plus sin 2 theta by 2, this limit. After simplification, we get pi minus 1 by 4. Result is proved. Question 9. Evaluate the integral, surface integral E square root of 4a square minus x square minus y square dx dy, where E is the region bounded by the circle x square plus y square equal to twice ax. This region E, region of integration, the set of all those points xy belongs to R2, such that x minus y whole square plus y square equal to a square. Because we can write x square plus y square equal to twice ax, so x minus a whole square plus y square equal to a square. And this represents a circle with center A0, this point A0, with radius A, is the radius A. X-axis, y-axis, this. Now changing this Cartesian coordinates to polar coordinates, x equal to r theta, r cos theta, y equal to r sin theta, and this, for this transformation Jacobian J, we know this equal to r, not equal to 0, except that origin xy equal to 0 0. So this circle x square plus y square equal to twice ax, and put x square plus y square equal to r square, and this twice a into r cos theta, so we get r equal to 0, and r equal to twice a cos theta. This is r equal to 0, this pole, and r equal to twice a cos theta. This is the circle, r equal to twice a cos theta. Hence the given integral becomes theta equal to minus pi by 2 d theta, and integration r equal to 0 to twice a cos theta whole root over 4a square minus r square modulus of Jacobian j into dr. And because this 4a square minus x square minus y square, this integrand is this 4a square minus r square. Limit theta tends to minus pi by 2 because when theta equal to 0 on the x-axis, is the main line is x-axis. When theta equal to minus pi by 2, and this is line negative y-axis, and from this theta equal to minus pi by 2 to theta equal to pi by 2. When theta equal to pi by 2, this line positive x-axis, so this theta ranges from this to this, and theta r ranges from 0 to the circumference of the circle twice a cos theta. So we can change this limit in this way, and this d theta has to integrate this, put 4a square r square equal to z square, so this minus z cube by 3, so you can write minus 1 by 3 4a square minus r square whole to the power 3 by 2, limits 0 to twice a cos theta. So when twice a cos theta, put r equal to twice a cos theta, so 4a square minus 4a square cos square theta whole to the power 3 by 2, and when r equal to 0, 4a square whole to the power 3 by 2, taking common minus 1 by 3. So 4a square whole to the power 3 by 2 is equal to 4 to the power 3 by 2, a to the power 2 into 3 by 2, that is 2 to cancel, so 3, and this 4 to the power 3 by 2 8, so 8a cube by 3, and this 1 minus cos square theta, 1 minus cos square theta whole to the power 3 by 2, so sin square theta, sin cube theta, and common 4a square whole to the power 3 by 2 is minus 1, so taking minus again 1 minus sin square sin cube theta, so 8a cube by 3 integration minus pi by 2 d theta minus 8a cube by 3 integration minus pi by 2 sin cube theta d theta, so you cancel 1 d theta cancel. Now this integration is 0 because we know integration minus a to a fx dx equal to 0 if f of minus x equals to minus fx, that is when fx is odd function. Here sin cube theta is odd function, so this part is 0. So integrating we get theta lower limit upper limit pi by 2 minus lower limit minus pi by 2. So after simplification we get 8a cube into pi by 3. This is the answer. Question 10. Find the value of the integration this over the volume, triple integration, volume integration over the closed volume. This indicates this round indicates the closed volume V, dx dy dz whole divided by x plus y plus z plus 1 whole to the power 4, where V is the volume enclosed within the tetrahedron formed by the plane x plus y plus z equal to 1 and x equal to 0, y equal to 0, z equal to 0. Now we use the transformation x plus y plus z is equal to u, and this x plus y equal to uv so x equal to uvw and this y equal to uv minus x equal to vw, so taking common uv 1 minus uv, and z equal to x plus y equal to uv. So u minus uv, so taking common u, so this 1 minus v. And this is the Jacobian for this transformation. This del xyz by del u vw, del ux, del vx, del wx, del uy, and del u, sorry, this is the del uy, del vy, del wy, del uz, del vz, del wz, and del ux from this over the x derivative with respect to u, so we get v into w here, and similarly others. And expanding this determinant, we calculate this equal to minus u square v. Now this Jacobian is negative except when a equal to 0 or v equal to 0, the same sign Jacobian for this Jacobian. That is when x equal to 0, y equal to 0, z equal to 0. Now when x equal to 0 means u v w equal to 0. So u equal to 0, v equal to 0, w equal to 0. Y equal to 0 means u v bracket 1 minus w equal to 0. So here u equal to 0, v equal to 0, w equal to 1, and z equal to 0, e equal to 0, v equal to 1. Also x plus y plus z equal to 1 means u equal to 1. So region of integration d, this volume x y z belongs to R3, x equal to 0, y equal to 0, z equal to 0, and this bounded by this plane x plus y plus z less than equal to 1. So actually this volume is this type, and this x axis, and this y axis, and this z axis. So this is the tetrahedron by this plane x plus y plus z, and this plane is x plus y plus z equal to 1, and by this plane x equal to 0, this yz plane, and this when y equal to 0 means zx plane, and the z equal to 0 means xy plane, and this plane x plus y plus z equal to 1, and becomes d dash u v w plane, and this r cube is 0 less than equal to 1, 0 less than equal to v less than equal to 1, and 0 less than equal to w less than equal to 1. Actually u v w plane, this becomes this actually this the forms a cube. On this y axis, this is the u axis, and this is the v axis, and this is the w axis. Is origin 0, so u equal to 0 to 1, and v equal to 0 to 1, w equal to 0 to 1. So this is the volume in this uv w plane. So closed interval, closed integration, volume integration toward d, actually d or v in this question is v, so we use here d, notation d here. This you can change this v to v dash, so you can change from v not d to v dash, this v dash, so accordingly change v and this v dash. So this integration of our v dash modulus of j du dv dw, and x plus y plus z equal to u plus 1 whole to the power 4. So this value is u square v du dv dw u plus 1 whole to the power 4. Integration separating this 0 to 1, u equal to 0 to 1, v equal to 0 to 1, and w equal to 0 to 1. And because you're separating this, because this u is constant integration, and u v r this integrand is, you can separate this. So for this put u plus 1 equal to p, So du equal to dp and u equal to 0, p equal to 1. So limit p equal to 1 to 2, p minus 1 whole square dp by p to the power 4. And for this part, this v square by 2. So v square by 2 from limit 0 to 1, so half, and from this w 0 to 1, this, so we can get this 0. Now p minus 1 whole square means p square minus twice plus 1 whole divided p to the power 4. So we can write 1 by p square minus 2 into 1 by p cube plus 1 by p to the power 4. So this integration 1 to 2 dp by p square minus 2 integration 1 to 2 dp by p cube plus integration 1 to 2 dp by p to the power 4. So this half into minus 1 by p integration 1 to 2 minus 2 into minus 1 by 2 p square integration limit 1 to 2, and this minus 1 by 3 p cube limit 1 to 2, and substituting all limits and upper limits after simplification, we get 1 by 48. This is the answer. Next question, 11a. If half this closed integration over C, this notation, circular notation, is closed integration over C. C is a closed curve, integration over the closed curve C. Bracket x dy minus y dx represents the area bounded by the closed curve C. Then find the area bounded by the curve x equal to a cos cube theta and y equal to a sin cube theta. Now this half closed integration over C, x dy minus y dx, here x equal to a cos cube theta, y equal to a sin cube theta, so dx equal to this and dy equal to this, and putting all these, x equal to a cos cube theta, dy equal to 3a sin square theta cos square theta d theta, minus y equal to a sin cube theta, and dx equal to 3a cos square theta into minus sin theta d theta. So taking common, 3a square by 2 sin square theta, and this cos to the power 4, so cos square theta bracket and cos square theta plus sin square theta, so this is equal to 1, and this is equal to 1, integration limit 0 to twice pi, this limit integration limit bounded by this curve this, so sin square theta equal to 1. Now sin square theta cos square theta equal to 1 by 4 into 2 into sin theta cos theta whole square, 1 by 4 sin square 2 theta is equal to 1 minus cos square 2 theta, half into 1 minus 1 plus cos 4 theta by 4, this is equal to 1 by 4 into 1 by 2 minus 1 by 2 cos 4 theta, so this is equal to 1 by 8 into 1 minus cos 4 theta. So we put here 1 minus 4 cos theta and 1 by 8 common. So 3 square by 16, this integration theta, after integrating this d theta 0 to twice pi, and this integrating we get sin 4 theta 4, limits 0 to twice pi. Actually this 0, sin 0 0, when sin 4 into 2 pi, this also 0. So from this 2 pi, so actually 3 square by 8 into pi, and this is the required area. Note that this integration over gamma p dx plus q dy equal to region R del q del x minus del y p dx dy. This is the Green's theorem. If we put p equal to minus y, q equal to x, then half of integration over gamma actually is the closed integration over gamma closed integration over gamma x dy minus y dx equal to half of double integration over r 2 into dx dy. So double integration r dx dy, actually this is the area bounded by the closed curve gamma. So half into integration gamma x dy minus y dx, this is the area bounded by this. Next question, 11b. Show that the vector field given by y sin z I cap plus x j cap plus x cos z k cap is conservative. Find a scalar potential of this field. Now first we find this curl f I cap, j cap, k cap, del del x, del del y, del del z, and these components of this vector f, y plus sin z, x, x cos z. And after simplifying we get this is equal to null vector. Hence vector f is an irrotational vector. Now we have the theorem: a vector field is conservative if and only if it is irrotational. So obviously vector f is a conservative vector field. Then we can find a scalar potential phi such that vector f equal to grad phi. So vector f is this. Grad phi means I cap del del x phi plus j cap del del y phi plus k cap del del z phi. Since I cap, j cap, k cap are linearly independent, so we can compare this from these both sides, these components of I cap and components of j cap and components k cap. So we del x phi equal to y plus sin z, del y phi equal to x, and del z phi equal to x cos z. First we integrating with respect to x. So phi equal to yx plus x sin z plus f1 is a function of yz. f1 is an arbitrary function of yz. And this integrating with respect to y, this phi equal to xy plus f2, a function of xz, is f2j, arbitrary functions of xz. And from this third, integrating with respect to z, we get phi equal to x cos z with respect to z plus f3 is a function of xy, is an arbitrary function of xy, f3. And for equality, for maintaining the equality, we choose f1 equal to 0, that is f2 equal to x sin z, and f3 equal to xy. Then we clearly get phi equal to xy plus x sin z plus some constant, arbitrary constant k. And this is the required scalar potential for this vector field, given vector field f. Question 12a. Use Stokes theorem to find the line integration over c x square y cube dx plus dy plus z dz, where c is the circle, x square plus y square equal to a square, z equal to 0. Now Stokes theorem states that let f be a continuously differentiable function over an open surface S with the closed curve C as its boundary. Then this closed curve C, closed integration over C, f vector dot dr vector equal to this open surface S curl f dot n cap ds, where n cap is the unit normal to S and the line integral is taken over the positive direction, that is anticlockwise direction over C. So for this xy plane, so this x square plus y square equal to a square, z equal to 0, so this is the xy plane. So this circular plate is the open surface, but this curve C bounded this surface S. So n cap is the outer unit normal, and this positive direction means, and this is the anticlockwise direction of this integration, is anticlockwise direction. So here n cap is along the z direction, so n cap equal to k cap unit vector. Hence this integration equal to closed integration over C f vector to dr vector. Now f vector is given by this, vector f equal to this. Hence S is a plane surface in the plane z equal to 0 in the xy plane, bounded by the circle x square plus y square equal to a square. Clearly n cap equal to k cap along the positive z axis, because here the rotation is this anticlockwise sense, because this line integration is anticlockwise sense, so outward unit normal this along the axis. So by Stokes theorem, this integration over C equal to over this surface integration curl f dot n cap ds. Now curl f equal to, we get minus k cap 3x square y square. So this minus 3x square y square k cap, and for this k cap is for this n cap for this n cap is k cap, so k cap into k cap equal to 1. So this, now this circle x square plus y square equal to a square, so limits of y, this y plus minus square root of a square minus x square, and when plus for this upper portion of this circle and for minus this lower portion of this circle, so y equal to minus square root of a square minus x square, and this square root of a square minus x square, this y square dy, and this x square is minus 3 common, this dx means this point minus a0 to a0, so x equal to minus a to a, this y cube by 3 and lower limit to upper limit, and simplifying we get this. Now x equal to minus a to a, and this equal to actually 2 into integration 0 to a, because it's minus a to a fx dx equals 2 into 0 to a fx dx if fx is an even function. Now here this x integrand x square into bracket a square minus x square whole to the power 3 by 2 is also an integrand is even function, because if we put x equal to minus x and no change in this integrand, so this is even function, so we can change these limits 0 to a, and putting x equal to a sin theta, so limits 0 to pi by 2 a to the power 5 sin square theta cos square cos cube theta, and for this dx a cos theta d theta, and this is equal to 4 minus 4 a to the power 6 integration 0 to pi by 2 sin square theta cos to the power 4 theta d theta, and this is the beta function, because we know integration 0 to pi by 2 sin to the power m theta cos to the power n d theta equal to half of b m plus 1 by 2 comma n plus 1 by 2 when m greater than minus 1 n greater than minus 1. So b 2 plus 1 by 2 4 plus 1 by 2, this is equal to 3 by 2, this is equal to 5 by 2, so b mn equal to gamma m into gamma n by gamma m plus n. So we get this gamma half equal to root pi, and using this gamma n plus 1 equal to n factorial if n is positive integer, and gamma n plus 1 equal to n into gamma n is any positive number. So after simplification we get minus a to the power 6 pi by 8, the correct answer. Next question, question 12b, apply divergence theorem to evaluate surface integration over s f vector dot n cap ds, where f vector is this and s is the surface of the rectangular parallelepiped 0 less than equal to x less than equal to a, 0 less than equal to y less than equal to b, 0 less than equal to z less than equal to c. Here n cap is the unit outward drawn normal to the surface S. Now Gauss divergence theorem states that let f be a continuously differentiable vector point function and S be a closed surface enclosing a volume V, then this triple integration over V divergence f dv equal to this surface integration over S f dot n cap ds. Here n cap is the unit outward drawn normal to S. Now divergence f equal to this f vector is this given So divergence equals to del dot a vector. So del means I cap del x plus j cap del y plus k cap del z, and a vector is this. So we get 2 into bracket x plus y plus z. Here P is the volume of rectangular parallelepiped and given by this x limits 0 to a, y 0 to b, and z 0 to c. Then by Gauss divergence theorem we get this surface integration, where this actually this equal to volume integration this 2 into x plus y plus z into dv. So 2 into limits x equal to integration 0 to a, y equal to integration 0 to b, z equal to 0 to c, x plus y plus z dz dy dx. So integrating with respect to z, we get x z plus y z plus z square by 2, z equal to 0 to c limit dy dx. First we put z equal to c, so this xc plus yc plus c square by 2, and this minus all 0. Integrating with respect to y, so this c into xy plus y square by 2 plus c square by 2 into y, limits y equal to 0 to b, so put y equal to b first, so xb plus b square by 2 plus bc square by 2 minus all 0. Integrating with respect to x, so x square by 2 b into c plus b square c by 2x plus bc square by 2 into x, limits x equal to 0 to a, put x equal to a. So these two in denominator common and this numerator 2 cancel each other, so we get a b c into bracket a plus b plus c. Question 13, show that the volume common to the cylinders x square plus y square equal to a square and x square plus z square equal to a square is 16a cube by 3. And this is the cylinder x square plus y square equal to a square. This is the vertical cylinder, axis is z axis, and this horizontal cylinder along the y axis x square plus z square equal to a square. And from the second part, x square plus y z square equal to a square, so z square equal to a square minus x square, so limit of z is this plus minus square root of a square minus x square. So for this horizontal cylinder, this limit we want to find this closed volume intersecting of these two cylinders. So z equal to minus root over a square minus x square to plus root over a square minus x square. And from the first cylinder, this x square plus y square equal to a square, so y square equal to a square minus x square, so y equal to plus minus square root of a square minus x square. So from this vertical cylinder, this range of y, this y equal to minus root over a square minus x square to y equal to plus root over a square minus x square, and the limit of x is minus a to plus a is the limit of x. So this required volume is this integration x equal to minus a to a dx, integration y equal to minus square root of a square minus x square root over a square minus x square dy, and integration z equal to minus root over a square minus x square to root over a square minus x square dz. So from this last integration z, so we get integrating this, and after simplifying this 2 into square root of a square minus x square into dy. So this no function here y, so this constant when with respect to dy, so only we get y, this lower limit and upper limit, so we get 2 into root over of this, so 2 into 2 4, so 4 into a square minus x square into dx. So integrating and simplifying, we get 16a cube by 3 is the required answer. Thank you. This completes the question 2021 Group C Multivariate Calculus 2, and thank you for watching this video.